All right. Good morning, everyone. My audio's a little bit quiet. Let's try to turn it up. All right. So welcome to the next lecture in Data 100 on EDA. Please sign the Slido if you haven't done so already. The last lecture, I went a little bit too slowly. So today I'm going to pick up the pace. We need to finish data wrangling in EDA. Then we're transitioning to text wrangling and regular expressions. So at the end of last lecture, we were talking about types of variables. This is an important topic. It's important now for how we approach our data processing, how we understand our variables, and it'll also be important as we think about visualization. And in the end of last lecture, we introduced this tree, a way of thinking about the variables that we are working with here. Oh, 1 second. In Data 100. So we talked about a variable can be quantitative. And this is, again, not how the data is stored, but what kind of data it represents. And quantitative variables can either be continuous variables or discrete variables. Continuous things are like price, maybe temperature. Discrete things can be years of education, number of siblings, things for which fractions don't make a lot of sense. In previous years, we made a distinction between these two classes here. For this semester, you'll still learn about this distinction, but we're going to try to focus on kind of this big category of quantitative. On the right side, this distinction becomes more important. So we'll talk about qualitative variables. These are things that are categorical. There are two classes, ordinal and nominal. Nominal variables are like names, maybe your political affiliation. It could be a number, but it's a number that's representing a name. Where the actual order of numbers doesn't matter, where differences between cal IDs don't mean anything. And then ordinal, this type of qualitative data, this type of categorical data, is often the most confusing. And these are names that have a meaning in their order. Things like preferences, maybe levels of education. First year, second year, third year. They're names, but they're ordered. So at the end of last lecture, we didn't get to do this, but this is a good way to think through these kinds of types of variables. Let's try to answer these. So CO2 level in parts per million. You're doing science, studying the atmosphere. Qualitative or quantitative? Quantitative. Continuous or discrete? Continuous. So we'll say this is A. Number of siblings. A, B, C, or D? B. It's discrete. It is a number. We could compute differences. You can have difference. This person has 2 less siblings than this other person. GPA. A. It's continuous. You get a floating point number, a fraction. GPA is a little tricky, though, because technically it's computed using A, B, C, Ds, which are converted to numbers and an average over years. So it's still, we think of it as continuous. You kind of see these are sort of fuzzy, whether that's discrete or continuous. Income bracket, low, medium, or high? C. Why? Well, there's an ordering to these. If you're building a plot and you plot the bar graph and you have a low, medium, and high, and you do low, high, medium, that's ridiculous. Don't do that. There's an order to those variables. C. Race or ethnicity. D. Nominal. There's no ordering, just names. D. Shirt size. Small, medium, large. C. Good, C. And Yelp star rating. This was last week's poll. Let's do it again. Just maybe build in. Okay. We got the right answers. Yelp star rating. All right, so you're voting. I'm going to talk about it because we're behind. Continue voting. There isn't really a concrete right answer to this. It could be a couple of things. If we're really digging into what it means to be a star, 5 stars, 4 stars, 3 stars, they have very different meanings. Isn't like 4 is a little bit less than 5 or 3 is a little bit less than 4. Some people are like 4 and 5 is a lot, and then 3 is, I did not like this restaurant at all. It's gonna be different things to different peoples, different gaps between them. Could suggest that they're ordinal. That might be a reasonable way to think about them. Might be reasonable. When we build models, we'll often do regression on things like Yelp stars. We'll treat them as a quantitative continuous entity. And that's also somewhat reasonable. So it could be both. And when you're doing your analysis, you might take a mix of both. If you're trying to visualize these, maybe the right way to compute a star to describe what's going on at the star rating for a restaurant is to look at the histogram of the star ratings, or a bar chart of the star ratings. Right? Or I give you the average. It's 3.6 stars. There's a lot more information in that histogram. I might treat that as a discrete thing, where again, I'm reporting the magnitude of each of the different star categories, or I might just give you an average and a variance and so on. So some of these are tricky. When I model this, I often treat this as ordinal, but it could also be treated as continuous. So more than one interpretation. Should probably do this in reverse order. So this is one of my favorite restaurants on campus right now, Mine Coffee, excellent coffee shop. I don't get discounts there, but I should. If you look at their ratings, right, I can give you these two visualizations. This is treating it as just a quantitative continuous thing. This is treating it more as an ordinal thing, right, where I'm telling you the counts of each of the categories. Decide which one is more informative to you. All right. So this wraps up this long discussion we spent most of the last lecture on around the structure of data, what's its shape. We talked about different types. I should bring this in right now. So we talked about different formats, recursive formats like JSON, these nested representations of data. We talked about records, it's being nested. How do we define a record? Is it a row? Is it a part of a JSON object? We talked about unnesting records when you're working with these complex data types, finding records inside of records and maybe expanding them into more fine-grained things. We talked about granularity. We talked about data referencing other data. So you have lots of tables. You often need to join across those tables. So when to merge, when we need to get external data. We just wrapped up talking about fields. What are the columns? What do they represent? The various types. Okay. So both how they're encoded and the type of data that is in that column. All right, so I want to wrap up the end of this EDA lecture by talking about scope and temporality, which are a bit quicker. So scope, which we'll talk more about with sampling, is what does the data reflect relative to the population I'm thinking about? So I'm interested in this population here. My data maybe looks like this. That's a pretty common case, where sometimes I have parts of my data that I don't want. Maybe I want to filter those out, and then some parts I have the data I do want. They reflect the thing I'm trying to study. Pretty common when you're doing EDA. Trying to figure out what your data looks like relative to the population is a real problem. In an ideal world, you get something like this. You have everyone, but you're interested in only a very small subset. Everyone. It's inside of your data. But that's pretty rare, where you have everything you possibly want. So my data is too broad. Can certainly do filtering. I think when we're in this setting here and I do filtering here, I might find that the data I'm dropping is a large fraction of my data. And it could be that my sample is biased. It only took this little bottom corner of the population, and that's something I have to deal with when I think about my sampling process. So we'll come back to scope when we talk about sampling. But in EDA, you're trying to understand, what do I have and how does it reflect the population I'm trying to study? A big part of scope is the position and time, so temporality. Unfortunately, in this class, we don't actually spend enough time on time, but dealing with data, often we're dealing with what would seem like a snapshot in time, but it's not. We take a survey of students at the beginning of the semester. You can answer that survey anytime at the beginning of the semester. Your opinions might change. Big events in the news could happen to change how you look at the world. So my data is often not a snapshot in time, but some measurement across time. There's often dates in that. I have to think about that date, the dates. There's periodicity in data. Time is cyclic. We have days, hours in a day have different meanings. Days of the week have different meanings. So to deal with the time in the place where it's located and the periodicity of that data. You often have time and date fields in your data. What do they really mean? Is it when the event happened? Like patient, checked in sick, timestamp. Is that when the nurse decided to enter that information, in the evening when he was checking out of his shift? Or is it when the patient actually entered the shift or entered the hospital? So what does the event mean? When was it entering the system? So was it when it was collected, entering the system? But often we'll have timestamps that are added downstream. So people do some processing of your data. They pull it from the central bank in one country and copy it to the data warehouse in another country, and they put a timestamp on it. The timestamp has nothing to do with the underlying data, but has to do with when the data was transferred and maybe what process was used to transfer it, which could affect the meaning of the currencies and so on. So understanding the meaning of timestamps in our data is very important. Principles and techniques. Those are some principles. Here's some techniques. You're going to use the datetime object in Python, the DT accessors, pandas. This makes it easy to work with dates and times. Think about things like time zones. You have to know when the date was recorded to actually convert to the correct time zones, and so on. Any questions so far? I'm going fast. Who's heard of Unix time? Okay, very few. This date, so important. It's the beginning of all time for computers. It's Unix time. When you have a 0 in a date field and you convert it to one of these datetime objects, it's January 1st, 1970. It's very important to know. When you have all these dates, January 1st, 1970, it's probably you have weird data. Understanding that this is an important time in computers, it's important. So you're going to see strange null values and dates. All right. Faithfulness. How well does the data capture reality? This is where it gets fun. So it used to be this was a very common problem the day you would process. Today, we have better data tools, so it's less common, but it still happens. People put stuff in Microsoft Excel and then export it out again. It drops columns. Maybe the data was too big for their Excel, so they only pulled a sample of the data in. Now your data's been filtered. Used to be that if you had 65,536 rows, that was the Excel max of rows. It's gotten better, so you don't have this issue anymore. But this could be, when people touch your data, they might be filtering stuff out. You need to be able to recognize that. This happens a lot. You'll often have duplicate records, duplicate fields. You use Google Forms. People enter the thing twice. Now you have 2 votes for students. You have to deal with that. So you have to identify duplicate rows, maybe use something like a primary key, like a student ID, and then duplicate columns. You add an extra field to the Google form at some point. You might have a column repeated twice. So you have to pick which is the correct column. Spelling errors. People manually enter data they can't spell. Checking for things like addresses, names. You'd be surprised. In medical records, doctors can't spell medicine names. So you have to deal with that if you're processing electronic medical records where they were allowed to type in the name directly. Units not specified, currencies, measurements, weights. All these things could depend on where the thing was taken and what unit system they use there. To figure out what they are, or maybe convert them. We already talked about this, time zones, big issue. Missing data, I already talked about January 1st, 1970. 2000 could be another way of encoding zeros. Often people will use just a blank to encode missing values, but sometimes they'll use something like 999 or -1 as a temperature or weight. Some people will write 1, 2, 3, 4, 5 in a Google form to say, I didn't want to fill in this field, right? To detect these weird things. If you're lucky, it'll be not a number. like a nice computer way of saying I don't have a number, or null, which is what the database community would say when something's missing. All right, this is important. Normally I'd spend 30 minutes or 20 minutes on this. We're gonna go a little quicker. What to do with missing data? What should you do when you have missing data? So suppose I have a record with some missing values. Student forgot to give me their email address. Probably, this is very common. What's the most common solution to it? In fact, it's built into pandas. You can do .drop NA. Just throw away those rows that had missing data. Makes life easy. Who needs rows with missing data? Just make your data clean by dropping all the bad stuff. Problem, often the bad stuff is the good stuff. People forgot to fill something out. Maybe there's a reason. We actually, when I first started doing this, ran into issues with food data, which I think is in one of the assignments, where things were dropped when we first did the analysis because it was missing something. Turns out that missing something was really important. The fact that it was missing it was important. Right? It could be corrupt records. Maybe if you have a handful, like less than 20%, less than 10%, you could probably get away with dropping it, but you should think carefully about what you're dropping. So one very common solution, drop records. What I like to do, keep records. Keep that information there and work within your downstream analysis. Maybe make an extra column where you do something like imputation. You guess what the value could have been, should have been, for missing values. There are a couple ways to do it. Average imputation, pretty standard. Missing someone's GPA. Plug in the average GPA for students in the class, use it for downstream analysis. Okay. Some risk in doing that. What's one way to deal with it? Which average? You could be a little more clever and find a related subgroup. Similar students, similar year. Take an average not from the whole class, but a smaller segment. Other strategies, cool names like hot deck imputation. What does this mean? Randomly pick someone else's GPA and just plug it in for the student's missing GPA. Sounds crazy, right? But I can do this many times, and I can run my analysis with different samples and see, well, if I had some distribution of outcomes for that one student, how would it have affected my downstream analysis? So I can measure how robust things are. We'll talk about this later in the class. I could use regression, more predictive modeling techniques to try to fill in the missing values. These are all pretty advanced. Yeah, and so if we talk about hot deck, we can go further and do things like multiple imputation, repeated analysis to figure out how robust my conclusions are with respect to whatever imputation I do. All right, so these choices will affect things like bias, uncertainty, quantification. Certainly this here is going to introduce bias, and this could affect uncertainty. Maybe the most important question you should be asking yourself, why are the records missing? You get to be a detective. Why is it missing important fields in the crime data for the city of Berkeley? Why did they not add that information? If we had time, we'd go through this demo. It's a fun one. The notebook is there, so I actually encourage you to take a look at it. It's pretty straightforward. This is data from Mauna Loa. And here's a plot of the CO2. This is average CO2 per month through time. Temporality. See this zigzag going on? What is that? It's the Earth breathing. Every year CO2 rises and falls with algal plumes in the ocean. What is this business here? I'll tell you this is negative 999. We had negative 999 parts per million CO2. This is a missing value. If I hand you this plot, you're like, wow, something's going on with that visualization. What should you do? Drop missing values, not a bad idea. Get a plot that looks basically the same because it's so zoomed out you can't see the missing values here. Right? Maybe most of my analysis works out. It's like 2 or 3 missing values here, 1 or 2, 1, 1, not a big deal. Or, as a scientist will do, they interpolate. We use models to fill in those missing values. We get a nice smooth curve. get the missing information right here, based on the patterns in the data. Lets me do downstream analysis. Questions? Good question. I'm making up data. That is dishonest. It is. I should tell you that I'm making up data. So when you do imputation, you shouldn't go ahead and this is the truth. It is not. You've imputed. You need to say that. When you're doing analysis, if a lot of your data is missing, it might be helpful to impute and then use that as a feature for some downstream tasks. Don't lie. Tell people. Oh, good question. And for those on Zoom, if I use imputation, am I making things up? Kind of. Is it lying to the person who's looking at this data? Kind of. If I don't tell them, you need to report what you did. You need to say, I was missing this information. I imputed it using these techniques. I did analysis to the effect of that imputation. And with that imputation, I could make much better predictions. That's why I did it. If you drop those records, you might want to say that too. A bunch of students didn't enter their preference for section, so I dropped them. Maybe they're all grad students, so I dropped all the grad students. That might have been a mistake. Okay. All right, we're done. We did it. So, end of the EDA discussion. We talked about going through your data. Look at your data, look at the metadata, timestamps, anything you know about the data. You should read the manual, but don't follow it too closely because manuals are often out of date. Look at each field. I go one field at a time. What is it? What's its type? What's going on? What's missing? So on. Look at pairs of fields. What are the relationships between them? This makes way more sense when you have the tools of visualization, which are next lecture. So you're going to visualize each of these steps as you go through it. You're going to check assumptions. Students should have a GPA between 0 and 5. They're -99, what's going on? Address anomalies. Maybe I need to impute, maybe drop records, maybe fix spelling and so on. To the person who asks, is it lying? Record everything you do. Record that whole process. So you can tell the full story of what you did and think about its implications on your final conclusions. You did it. So that was the end of text wrangling, or the end of EDA. Now we're going to talk about text wrangling and regular expressions. Are there any questions? The basics of EDA. Okay, go on. So you finished EDA. Kind of. A big part of EDA is going to be working with text data. And we didn't have this in the first cut of this class, but in subsequent versions, it became one of the more useful parts of Data 100. I'm about to tell you about how to work with strings. You don't often get this because it's in the weeds, but it's also pretty critical. So we're going to also talk about regular expressions, a terrible language for everyone. And then next lecture will be fun stuff like plots. All right. So working with strings. Strings, just text, working with text. I'm going to talk about standard text manipulation tasks first, and then the technologies we use to do these tasks. And I'm going to teach you an entirely new programming language in this lecture. All right, so why do we work with text? 2 common use cases for working with text. 1, canonicalization. Spelling errors, variations in how people write addresses, make it hard to do analysis of who lives in Berkeley if people spell Berkeley differently. Sometimes they capitalize, sometimes they're missing an extra E. Canonicalization is converting my data so that it has one possible form. Should make a new county column. It's a little bit wrong. Maybe a new county column with counties in some more canonical form. Fix spellings, drop punctuation that could be distracting when I'm trying to do visualizations and so on. It's also important if I want to join pieces of data, right? Different data sources have different ways of encoding the same piece of information as a string. So here I'm trying to join the counties. If I want to join them, I'd like them all to be in some very canonical form. I've gotten rid of spaces, I've gotten rid of everything, so there's a good chance that these things will now be the same across my 2 different data sources. So we can see that. So that's one reason. The other reason to do all of this to extract information. It's also pretty common. You'll get something like this. Could be in one of your columns of your table, you have this giant string, which contains some important timestamps. How do you pull that timestamp out of that string? Pretty common problem. So both these will show up in the data analysis you do. In fact, if you use Google Forms, you'll spend a lot of time with stuff like this, where people can answer, multiple selections. Google Forms just takes all the strings they answered and puts them in just one long string. You have to extract, which major they are, which classes they've taken, and so on. So that's a bit of extraction as well. All right, so we're going to use Pandas string methods. Start with that. In fact, we should start with the Python string methods. So base or just vanilla Python has ways to work with text. These are called string objects. And recall, and we'll come back in a second if you all recall this, but recall, if you have a string s, let's say s equals hello. That's my string. Okay, then I can say string dot lower or string dot upper. That changes the case of all the letters to lower or uppercase. I can do things like replace, where I put some magic in here, which we'll teach you today. So I'm going to replace parts of my string. I can split a string. Why would I split a string? Or you want to split it out into separate words. So I'm going to split on this little space right here. So I can split strings into lists. I can take substrings. What's this going to do? It's going to take this string from position 1 to position 4, inclusive, is that right there? Like that. So pull out the subset of characters from my string. Sorry, 4 exclusive. So skip the first character, put a few more characters in. I can do things like membership in Python. So I can take a string, and I can say in another string and test to see if AB is in S. And I can take the length of a string. All right, so standard Python operations. You could, and often, when you're first trying pandas, you could write a function, apply it to each row using string operations. That would work, but it'd be slow and hard to read. So pandas has some magic. .str. It's the .str operator. And you can take any series. You have a series object, so any column, single column, that contains strings, and do .str, and then apply a string operation to all the entries in that column at once. So my data frame as populations has a column called county. I can say .str, it's a string operators, lower, converts all the strings to lower. It's a little more interesting. Take the populations data frame, county column, string operator, replace all the ampersands with and. So there are many of these. You look on Google for Python series string, you can look at all the different operations you can call. Here's a short list, a few of them, and they try to mirror what you would do with a single string in Python, right? So you have string lower, string upper, you have string replace, string split, which will turn that column of strings into a column of lists. You can take a subset of each of the strings, or substring. You can check to see if the string contains another string here. You can compute the length of all the strings. There are more, but this is a pretty common set that you'll use in this class. I'm going to skip the demos until the end of lecture to make sure we get through everything. And then at the end of the lecture, I'll show you each of these pieces. If we don't get to all the demos for this lecture are really short. So you can scroll through them pretty quickly on your own as well. But in the demo, we'll talk about how to go from this and this to some common representation and join the two tables. Actually, I will highlight from that demo the code here. Let's do that real quickly. So a common pattern in writing these long string operations, again, is to use these parentheses. I have my data frame, and now I'm going to do a sequence of string operations one at a time. So first, I convert everything to lowercase. Now everything's lowercase. I replace all the spaces with nothing. quote, quote, a string that contains nothing. That is deleting all the spaces, so removing the spaces. Then replace all the ands with and. So now I don't have any ampersands anymore, just and. Get rid of all the punctuation. Now, get rid of all the periods by replacing it with nothing, the way of deleting the punctuation. I don't want the word county or parish as well, so I delete those, replacing with nothing. I will confess that most of what I do with string manipulation looks like this. It's pretty easy to read. It's a sequence of transformations I'm applying to all the strings, one step at a time, until I get to a string. It looks kind of like this, which is not amazingly readable, but is now consistent across all the different ways that it could be written. Yeah, so instead of Saint John's having a period sometimes not having a period, I got rid of the periods. It's more consistent. It is canonicalized in some common form. All right. You can do that same activity to pull information out too. Again, this is how I would probably do this before learning about regular expressions. So I can take my line. This is a string, but this could have been a data frame, .str. Sorry. Could be df column .str, and then this sequence of steps here. So in this case, I'm taking the string. I'm going to split the string here and take the second half of the string, so this whole part right here. Then I'm going to split the second half here and take just this part, and so on. So each of these steps, I'm peeling off parts of the string, trying to split it at different characters, and these characters have to be in that string for this to work. And I'm going to just keep splitting. So I split it here, then I'm going to split on these things, and so on until I get each of the pieces out of the string. Who finds this somewhat readable? Exactly. Only a few of you. It's a bummer. I would argue this is actually going to be more readable than what I'm about to teach you. But this is still confusing. So I'm going to show you in a moment a way to do this using a new programming language, which is how data scientists would typically do these types of extraction tasks. But it's good to know these techniques. And I think you'll find in practice, these are often easier to assemble. All right, so today we're going to talk about regular expressions for the rest of this lecture. All right, so I showed you all these kinds of individual calls that I can use to split strings up, but it won't work for things like I want to extract all the moon-like patterns. So I want to find all the instances of words that look like this in my string. So maybe I want to find all the ologies in my string. How do I find all the examples of someone mentioning an ology, like sociology, that they're studying? It's hard, maybe possible, but hard to do with these kinds of techniques here. So we use something called regular expressions, which are implemented in Python using the RE library, but also available in the string accessors. And here's just a taste of what this looks like. So if I want to find all of the strings that matched my log before, I just write this one little program right here. And at the end of this lecture, this is going to make a lot of sense. So it's a new programming language that you use inside of another programming language to match and extract information. So this is regex or regex. So regular expression, regx is how it's shortened, is a tiny programming language. It allows you to search strings for patterns. Start something really simple. This is a program that matches social security numbers. It says I have a digit between 0 and 9 3 times, followed by a hyphen, another digit between 0 and 9 2 times, followed by a hyphen, another digit between 0 and 9 4 times. I haven't explained any of the syntax, but you kind of see how I might be able to write something pattern in this weird programming language that would match something like a social security number. All right, quick aside, you can say regex or regex. The correct pronunciation is regex, but some people would disagree with me. So choose your favorite, but the correct is regex. So let's do this. All right, so first, you are not going to memorize this language. In fact, I can't memorize this language. I will constantly look stuff up for regular expressions. What our goal today is understand what you can do with the regex and how to parse and create a regex with a reference table. So don't be intimidated. High-level understanding, that's our goal. So some details. We're going to use a new vocabulary that you haven't heard of yet, of these kind of meta characters, especially escape characters, groups, and so on, to write down our regular expressions. You're going to use different kinds of grouping syntax. We'll talk about these. And you're going to learn about these different character classes and how to build your own. And we're going to get to how to use regular expressions in pandas. When I first started using regular expressions, in fact, it wasn't until this class that I spent a lot of time thinking about them. I found it confusing. And I found this website, which everyone has started to use as well, really helpful. So let's see, can I click on this? No. Turn off. Let's go to this website. It's a great website as you're going through regular expressions and you're like, what is going on? Go to this website. First thing you do is go on the left over here and click on Python. So use your Python syntax. Got this little R thing that'll make more sense in a little bit. And I can write my regular expressions up here. And I can write some test strings here, and it's going to show me where it matches. Do one really quickly. Cat. The cat. And the hat. It's in the hat, right? Cat in the hat. Doesn't work. Okay, maybe I go cat. Ah, matches cat. Great way to practice regular expressions. All the syntax we're going to cover in lecture here, you can play with over here. Keyboard. All right. Another source of material that I found helpful when I was learning about this regular expressions is this how-to guide for Python regular expressions. It walks through all the syntax I'm going to cover in this lecture. If you find this lecture confusing, maybe try this guide instead. And in the guide, it has little examples. You can copy those into your notebook and try them yourself. All right. The first 4 basic operations of a regular expression. Concatenation. This one's probably the easiest. You can write a sequence of characters like AAB, AAB, and that will match exactly that sequence of characters. We already saw that with cat. So AAB, AAB will match any string that looks like that. Any part of a string that looks like that. Get fancier. First operator. This is the OR. AA or B, AAB matches AA or BAAB. Not so bad so far, right? Let's keep going. Star. It's a pretty cool character. A, B, star, A matches 0 or more occurrences of the thing before it. So this matches A and no B's, A and 1 B, A and 2 B's, and so on. This is boring, confusing. It'll get more fun in a moment and more confusing in a moment. So we've introduced some very basic syntax. One more. Parentheses. It does what you think it should do. Kind of. Come back to where it departs as well. I put parentheses around AB and then a star here. That says this whole thing matches 0 or more times. So this pattern right here matches just A, because it's just A here, and 0 of these things. It matches AB, A. It also matches AB, AB, A, and as many ABs as I want, followed by, and there must be a terminal A. Questions so far? Surprised. Keep going. All right. These are called meta characters. They're part of our programming languages. These are just the characters in that language. A and B, C, D, 1, 2, 3, all those are just basic characters. These things here, they're special characters. What if I want to match a star? Use another character, which we'll learn about in a little bit. Put a slash beside it. Now that's not a meta character, that's just a star in a string. Keep going, we'll come back to that. All right, so we've introduced 4 operations. It's important to think about the precedence of these operations. So grouping, parentheses, has the highest precedence. So this means that the star applies to everything here. So again, this matches A, or any number of A, B, A, Bs. The star doesn't apply to just the B, it applies to both the A and the B. The star has a next order of preference, so it applies to whatever is immediately next to it. That's higher precedence than things like concatenation. So this is A, and then 0 more copies of B, followed by an A. So we do need parentheses if I want to have AB, this whole thing copied multiple times. The OR, that shows to concatenation. Concatenation has the next preference. This is 3, the order of precedence. So concatenation comes before the OR, which means the OR applies to all the stuff on the left and the right, not just the immediate characters. Okay. Let's do a poll and see how people are doing. So which regular expression pattern will match the string ABBA? Select all that apply. Vote. Who thinks there's more than one? Let's find out. All right. You got this. This is tricky. So let's walk through these. A, B, star, A. What is that matching? A. And remember, the star attaches just to the B, right? Order of operations. So that means A, and then 0 more Bs, followed by an A. So A, B, B, A, that works. Let's look at the next one. It looks like it should work, but the parentheses say I'm going to have 0 more copies of AB, the whole group, followed by an A. So it doesn't quite get A, B, B, A. AAB, AAB doesn't match ABBA, and it has to match exactly that string. So it only matches AAB, AAB. And the last one, AA or BAAB. AA doesn't match ABBA, and BAAB does not match ABBA. Questions here? The back, yeah. Yeah, let's do this with regular expression. All right. So we have all right, we'll make more in a second. So we want to do A, B, star, A. So it doesn't match the whole thing because it's looking for the AB group. So the pair of characters has to occur together 0 or more times. This will match AB, AB, A. It'll also match just A. Okay. All right. Let's keep going. Oh, a more challenging one. Which patterns match moon? Moon. Your expression should match any even number of O's except 0. Don't match MN or MOON, the odd number of O's. All right, this one's fun. Who's got it? Who doesn't got it? It's hard to get. This one's tricky. Think about it. I want an even number of O's, even number of pairs of O's, even number of O's. And I must have at least 2 O's. Let's see. All right, many of you got it. Almost half of you got it, a little over half. This one's tricky. Let's first look at why the bottom ones are wrong. So the very bottom one, MOO star N, says match MO and then 0 more O's. So MON would be fine. MOON would be fine. MOOON would also be fine. You're not supposed to match that one. Okay, so that doesn't work because it matches something you didn't want to match. This is one of the challenges in regular expressions. You're often looking for a thing that will get just what you want and not the things you don't. Okay, let's see the next one. Next one says M followed by 0 or more copies of this whole group, OON. It's a group, parentheses, and the star means 0 more copies of that group. So that matches MN, MOON, MOON, that's 4 O's, yeah. So it'll match an even number of O's, but it also matches MN. And I said, don't match MN. Doesn't work. Last one is clever. It says M, you must have at least 2 O's, and then you can have 0 more copies of a pair of O's followed by N. So moon, MOON, works. And then if you want to add another pair of O's, you can. So it'll always be an even number of O's that are added. This was hard. Other questions? Yeah. Yeah. Let me see if I can, let's just go to the regular expression tool again here. All right, so we got M, O, O, what was it? M, O, O, all right, yep, there you go, M, O star N. So we wrote, we got moon, moon, M, O, O, N, M, O, N. Okay, so we don't want to match, any of these. We did want to match M, O, O, N, M, O, 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 N. Okay. So we wanted all of these. That's good. So we got all the good ones, but unfortunately we got some bad ones too. Why did we get the bad ones? So you said M. Oh, so you have an MO. So we didn't get this one, which is good. So you had to have at least 1 O. But then you could have 0 more O's after your O. So you can have an odd number of O's. We don't want an odd number of O's. We just want even number of O's. Why do we want an even number of O's? I have no idea. It's just an exercise. You will find that you often have weird things that you want to get for real regular expressions you're trying to actually construct. Okay. Keep going. All right, so I have links to examples of each of these you can work through. This bottom one is extra fun, so you can think about what this regular expression is doing, and we will skip this for now. All right, so we're gonna learn some more operations. So a new character group here is the period. This is any character. So this matches any number, any letter, any space, any character. It's kind of the wildcard character. Square brackets. These build character classes. So this says match a single character that could be a letter between capital A and capital Z, or between little a and little z. So this little range thing is a way of writing a range of valid characters. So I could also do something like 0, 9. I might actually be able to do something like smiley face to sad face, but I've never actually tried that. Those are also valid characters. And what does it mean to be in the range of characters? If I were to put these characters in alphabetical order or in the order of the Unicode character set, all the characters between 0 and 9 inclusive, which in the case of numbers is all the rest of the numbers. All right, so this is a way of building a character class. This whole thing only matches a single a single little a, a single b, or a single little b. So it's a way of defining a single character that could be any one of these things. Another example could be something like A, B, C. That matches the characters A, B, C. And I can match that star 0 more times. Okay. We'll see some examples in a moment. The plus character. This is like our star, but instead of it being 0 more, it's 1 or more times. So AB plus matches AB, so there has to be at least one B, but it could be more than one B as well. The question mark, often called the optional, says that that character can occur 0 or 1 time. So A and B is optional. So A works and AB works, and that's it. Almost there. Squiggly brackets says whatever is before me repeated exactly X times. And it's the immediate character, same kind of precedence as all of these operations. Right, so in this case, it's saying I match an A and a B repeated twice. So it's equivalent to just saying A, B, B. Exact same thing. But you can get fancier. You say a range. So an A followed by 0 to 2 Bs. So this matches A, AB, and ABB. There is some redundancy in regular expressions, and that the star is exactly equivalent to this thing. You can do 0, comma. So 0 or more times. The plus is equivalent to 1, comma, 1 or more times. And the question mark is equivalent to 0, 1. All right, this is incredibly boring. That's why you're going to look at a table when you do this. But hopefully you've gotten some familiarity with some of the basic syntax and how it express or how to build a regular expression. All right, so we talked about character classes and we'll spend a little more time on that. So again, this is a way of describing any capital character, any number between 0 and 9. And this is saying any letter or digit. Arrange. And this represents just a single character in that class. So it's creating a class of characters. There's some other built-in ones that you'll use often. /W is equivalent to writing this, but this is hard to read. So you just say a word-like character, /W. So you're something like /W 1 or more times. You have a /D for digit and a /S for matching a white space. So a space could be 5 times exactly. So I want to match 5 spaces. Some crazy syntax. There's negation. So if I have something like, it only works inside of a square brackets. So if I have this square brackets followed by this negation operator, then it's the opposite of this. So this matches anything that's not a letter between A and Z in uppercase. So it's not an uppercase letter. All right, so you've seen character classes, a way of defining a character as some range of things it could be. And negation character classes, where I define a character as the opposite of something in this class. So anything that's not a capital A to Z. So if I did something like this, that's anything that's not a number. Anything. So long as that letter is not a number. I can match that 0 more times. I could also do this. Same thing. Anything that's not a digit. 0 more times. All right, and there's, because this is a common thing to do, negations, the capitalized versions of these letters here are the negated versions. So I could also just write slash big D 0 more times. Questions? Question in the back. Yeah, so why would I use this? I might say that I have like deer, and then, some people put 2 spaces in between. So maybe I'm going to do slash S 0 to 2 times deer. But if you put 2 spaces between deer and the next thing, I'm going to match that. You put 1 space, I'm going to match that. You put 0 spaces, you've got to put a space, I'll still match that too. So way of saying a space character. It could also be 2 tabs. So I could have 2 tabs that would also match. So a tab is another form of white space. But just do a slash T as a tab. We'll see it in a moment. All right, so let's go through a little practice here, and then we'll take a short break. All right, so this is saying I match any character followed by U, followed by any character, followed by U, followed by any character, followed by U, followed by any character. So that's cumulus, C, U, M, U, L, U, S, cumulus. You can do the exercise, could have also been jugulum, but not, what is this made up word? Succubus and tumultuous. Okay. Why does it match succubus? S, U matches. Up, I need 2 C's, I only get 1 C, 1 dot. Yep. All right, let's keep going. What is this here? This is a letter, a single letter. It's either a capital letter or a lowercase letter, followed by a lowercase letter 0 or more times. So word works, and capitalize works, but camel case doesn't work. So if you're a programmer, I can detect things in camel case or reject things in camel case with this regular expression. And I didn't allow for numbers, so for illegal doesn't work either. And what about this one? Kind of interesting. So this is J, followed by one of these characters, repeated 3 times, followed by HN. So that matches JAOEHN, June, but not this, because I needed 3 copies. And why not this? I needed 3 copies again. It's too many characters. Okay. How about this one? So J followed by one of these characters, O or U, 1 or 2 times, followed by HN. So again, matches these. Doesn't match this because 3 times and 0 times here. And this says I match J followed by at least 1 O and then HN. Do you see how I'm reading these? It's confusing. It's also really boring. You'll get a chance to do a lot of these in the upcoming assignments. All right, one more, and then we'll take a break. What pattern matches any lowercase alphabetic string that has a repeated vowel? Come on. Just pick one. Let's some hints. Matches any lowercase alphabetic string that has a repeated vowel. So we're looking for vowels. The vowel needs to be repeated. That's interesting. And lowercase, that's an important signal there. All right. We gotta go. So many of you got this right. What's going on here? Let's read the bottom one first. The bottom one says any character, lowercase, uppercase, repeated 0 more times, followed by a vowel 1 or more times, followed by, and it could be any of these vowels. So A, E would be fine. I repeat it, A and then E. So 1 or more times. A would be fine. Followed by any character repeated 0 more times. It's too general. Top one says any character between lower a and lower z, so any lowercase character repeated 0 more times, followed by, this is interesting, either AA or EE or II or OO or UU, it's a repeated vowel, followed by a lowercase letter repeated 0 more times. Okay, confusing? Play with it a little bit. Great, short break. We're gonna do a exactly 1 minute break because I'm behind schedule. So 1 minute break, stretch, get some water if you're at home. All right. I'd pretend like that was about a minute. Let's get back. We're going to finish this saltine challenge of regular expressions. It is a boring topic, but it's so important, and it'll get more complicated in just a moment. Oh, man. Just as a fun interlude, I believe this is a valid regular expression for email addresses. Regular expressions can get gnarly. We'll talk about that in a second. Oh, there's also this fun game, Regex Golf. Check it out. Basically, you're given some things not to match and some things to match, and you have many, 3 hits, 4 hits, however many attempts it takes to get to the expression that does matches everything you're supposed to match and nothing you're not supposed to match. Good game. All right. So now we're going to talk about greediness. Suppose I have this situation down here where I have all these divs. This is common when you're processing things like an HTML string. And I just want to get all the things inside these divs. I want to match this stuff. Pull out the divs. You might think that something like this would work. I can say div followed by any character 0 more times, followed by div and div. That should work, right? Let's try it. Okay. This is example of greediness in regular expressions. So here's my regular expression. It's a valid regular expression. What did it do? It said div followed by, well, it said any character 0 more times. That's another character. That's totally good. That's good. That's good. That's also, that's good. That's good. That's good. Those are all good characters. Good character. Ah, there's end of div. But I just wanted it to match this thing. Just want to get that one and maybe this one. Regular expressions are greedy. The dot star just keeps eating characters until it has no more choices left. The only way to end it is a slash div. How do I fix it? Let's learn how. And go. Here we go. All right. So the way to read what's happening here is I'm looking for the exact string div, then I'm looking for any character 0 more times, and then I'm looking for the exact string close div again. I'm going to find the longest thing that matches that pattern. So I grab this whole thing instead of what I wanted, which was each of these segments. So to fix that, we can use the non-greedy version of star. That is this. It's not exciting, really confusing, but all right. So we now say div followed by any character 0 more times, but don't be greedy. If you can end it with div, end it with div. This will fix it. Let's try it. What's my syntax here? Question mark. It works. It's magic. So you want to see what just happened there? It says, don't be greedy. If you can finish it with the rest of the regular expression, do that. Don't keep using this character that matches everything as many times as you can. So this thing here, this question mark, made it not greedy. Greedy? Not greedy. Questions? It's confusing. Play with it a little bit. All right, last of the rules. There's another way to do this. I just want to show you another way. How else could I match this thing? So this is greedy. I'm going to try something a little bit crazy. What if I do not this 0 more times? How does that work? This says match div followed by not a left then sign. So anything that's not a left then, and then div. Kind of works, right? What if I do this? Breaks. So we want to make it even better. What could I do? Leave this exercise. There are more than one way to implement regular expressions. In this class, the easiest way for doing something like this is I want any character 0 more times, but don't be greedy. So question mark. Okay. All right, let's keep going. All right, the last set. I promise, I hope. Okay, yes, I do. I do promise. I told you this earlier. I can put this slash beside something. So I said earlier you could put a slash star. This says read the thing after the slash as just a character. So if I want to match A plus B, it's right here. If I put the plus in my regular expression, it says match A 0 more times followed by a B. No, I don't want that. I want just the letter plus. So I put a slash right there. That converts the letter from this meta character to just a regular letter, like A, B, C, so on. Double use. Okay, so we have this character here, which remember we had before meaning not A, for example. If I put it outside of these brackets, in fact, I can put it at the beginning of a string that says I need to match A from the beginning of the string. So it will no longer match 1, 2, 3, ABC. It'll only match ABC at the very beginning of the string. Almost there. Okay, so remember, this has different behavior, whether or not it's inside or outside of this character classes, these square brackets. All right, one more. $, ABC money. Only matches ABC if it's at the end of the string. So will not match ABC, but would match if I put an ABC here at the end. Okay. Some practice. These are pretty straightforward. So arc only matches when it's at the beginning, not when there's a character before it. Arc $ only matches when it's at the end, not at the beginning. And slash converts this star. This no longer read this as a /0 more time, or sorry, it's no longer a special character, which is anything. Instead, it's just the period. So this only matches cal.com and not cals.com. If we got rid of this slash, it would match both of these. All right, questions? Okay, we're almost there. Let's start using this stuff. Okay, so you're going to use these in your assignments. First thing you're going to learn about is raw strings. Raw strings are written with an R followed by your quotations. This is just like your regular strings in Python you've been writing all along, but now you put an R at the beginning. Why raw strings? Well, if I don't put an R, then Python itself starts interpreting your characters. So you put a string in Python, you put a /s, Python interprets that as a special character. I don't want that to be a special character. If I didn't put this R at the beginning, I'd have to add a slash to protect the slash, and another slash to protect another slash, just that the original slash was there. So you don't want the Python interpreter doing string manipulation on your string. You want it to trust me, this is the string I have. Read it as it is verbatim. It is a raw string. So whenever you're doing regular expressions, because all these slashes will confuse Python, just put R at the beginning. And you can do it with a string like this. You can do it with a string like that. You can do it with your triple quote strings. Works on all the strings. Raw strings, probably your first source of bugs when you start doing this stuff in Python. You can read about the \plague later. All right. Regular expression library, RE, is the kind of basic outside of Panda's way of doing this stuff. And it takes, regular expression find all takes some pattern, which is my raw string. So here's my raw string pattern. And here's some text right here. And if I say find all of my pattern with my text, it's going to return a list of all the things that match to my pattern. Really useful. Now I can start extracting stuff in vanilla Python. But we're here in Pandas land. So if you have a series, use the string access, so you say .string, and then you say find all again. You don't need to pass text in because it's each entry in that series, each piece of data, you're going to apply the pattern to each of the entries in that series. So I can take social security number column, say string.find all, pass my pattern, and it's going to extract, oh, I don't have the output, here we go. It's going to extract all the instances of social security numbers in each of the column, or in each of the rows. So now you can start doing extraction in pandas using string find all. Capture groups, the last big concept, and we're going to finish on time, which is great. I told you parentheses are what you'd expect them to be. Parentheses, they group stuff together. There's one caveat. They do a little more than just put stuff together. They define a capture group and allows us to pull parts of a regular expression out of a bigger regular expression. So extract only the portion of the regular expression inside the capture group. So here's an example of one. Here's my string. I will meet you at 8:30 p.m. tomorrow. My regular expression says any character, 0 more times, followed by, and this is in parentheses now, 2 digits, followed by a colon, followed by, again, in parentheses, 2 digits, colon, in parentheses, 2 digits, parentheses, and then any character 0 more times. When I call find all now, it's going to do something pretty cool. it's going to return a list of tuples where it's pulled out each of the things into separate substrings. So now if I want to pull out an email address, and I want the first part of the email address, and then the @ and then I want the Berkeley, which is the domain, I can start to use capture groups to pull out pieces of a regular expression, not just the entire expression. Right, so you notice the output doesn't contain these things. So they weren't inside of a capture group. So no colons in my answer, just the numbers. Those are capture groups. This will become confusing because sometimes you'll want to use parentheses, but you don't want to capture stuff. There are tricks for dealing with this. You can read in the Python docs how to turn off a capture group from capturing. In practice, I found that generally the things in parentheses I ended up wanting to capture, or if I didn't, I would just ignore this thing and focus on the stuff that I did want to capture. All right, so let's start looking at some more Python pandas expressions for doing this. So we have an extract function, and this is useful because it works with these capture groups. So here's my capture groups, and it'll turn them into separate columns. So if I take my social security numbers and I give it, again, this regular expression, it's a raw string right here, it's going to extract 3 columns into a new data frame with each of the piece of information pulled out of my string as separate columns that I can work with. I'll have to rename those columns. It was called 0, 1, and 2. I give them meaningful names, and I can go on with my data analysis. So it's a very useful tool. And then there's extract all, which is even more powerful than extract and a little more confusing. Works the same way. I give it this pattern as before. But you'll notice here in this row, I had 2 social security numbers. Extract just finds the first match and returns it. If someone has 2 ology majors, I want to extract both their ology majors, then I would use extract all. And this does some pandas indexing magic where it returns 3 rows, and one of those rows is has a sub-series inside of it, which is the corresponding extracted social security numbers for that one cell. This is a nested index. Here, it is confusing. When you encounter the situation, there are tools to convert these into separate rows and work with each of the social security numbers separately. We're not going to cover that now. All right, last bit of information. These are useful. Like I said, we'll often use these patterns to delete stuff like remove divs, HTML notation, and so on. We can define our regular expression for the things we want to remove. And then we say substitute the pattern. And then a very common style of doing this is just begin quote, close quote, which is substitute whatever this thing, these divs, with nothing. Delete them from the string. That's what it'll do. And you can do the exact same thing in pandas with your replace function. Annoyingly, you need to tell it that it's, in fact, the pattern is a regular expression. Why? This function is so common and very few people are comfortable with regular expressions that by default, it doesn't assume the pattern is a regular expression. So when you're using this with regular expressions, you should say with regular expression equals true. All right, so an example here, again, I'm removing all the HTML tags from my HTML strings. So these are my HTML strings. Here's resulting text without tags. All right, so here's a final list of the important functions for string manipulation. When you on the exams, we'll give you the key piece of notation as a reference. You don't need to memorize all these functions, but you should be familiar with the kinds of things that they do when I show you a list like this. There are a lot of limitations of regular expressions. They can be, as you've already seen, pretty confusing. They get pretty complicated, but yet they are one of the more powerful ways for working with complex strings, and they're also very efficient for lots of string manipulation. All right, I think that is it. We've finished regular expressions. Probably the driest lecture of the semester. Next lecture is visualizations, one of the more exciting lectures this semester. See you all.